Hello everybody. So in the last couple of videos we have been looking at inferential statistics and some concepts. Um, and we spent a few weeks looking at those concepts. Now we're going to start the last major part of our course and look at some methodologies. And this first thing that we're going to look at deals with correlation. So our goals for this module are to distinguish between univariate and bivariate distributions, which you actually already know that, whether you realize it or not. Explain the meaning of positive and negative relationships. Construct a scattergram for a bivariate distribution. Compute a product moment correlation coefficient for a bivariate distribution. Determine the degrees of freedom in a test of correlational null hypothesis. Define and compute the coefficient of determination. Demonstrate an awareness that correlation does not imply cause and effect. Determine the appropriate sampling distribution statistics and compute a confidence interval for the correlation coefficient. And then finally compute and interpret a rank order correlation coefficient. And we will just introduce this concept. So with that, and these sound pretty reasonable, so we can get this done. Let's begin with what a correlation is. So up to this point, we've concentrated on statistics dealing with populations and samples consisting of measurements on a single variable. And what we mean by that is we've looked at GPA, we've looked at ACT scores, we've looked at height, the number of widgets produced in a day, all those kinds of things we've been looking at, we're going to call univariate distributions. So when we spread the height of our class out and tried to figure out what percentage of people are taller than I am, what percentage of people have an IQ greater than 120, all that kind of stuff, we were looking at univariate distributions. Often we need to consider relationship between two variables, such as the number of hours studying and the GPA, okay, or the number of absences a student has in school and their ACT scores, or compare GPA scores and ACT scores. So when we're looking at two separate variables such as this is known as a bivariate distribution. Okay, and we're going to see a lot of similar things with the bivariate distributions that we saw with univariate. We're going to talk about and use some of the same terminology, but we're going to do it with slightly different angles, considering it's the bivariate and we're using two variables here. So the correlation analysis does two things for us. It answers these questions. Is there a relationship in the distribution that we're looking at, the bivariate distribution? And if we determine there is a relationship, what is the direction of this relationship? In other words, is it a positive or is it negative? And I'll explain to you in just a minute what we mean by positive and negative. Not good and bad. So the first question, is there a relationship? We're going to answer by finding what we call the correlation coefficient, or simply R. Okay. So when you see R, and you will get a list, you have a list of all these symbols we're using for statistics. The R simply stands for correlation coefficient. The second question then, what is the direction of this relationship, is answered by the sign of R, whether R is negative or whether R is positive. And so to put it very simply, our correlations are going to range from a negative 1.0 to a positive 1.0, with a correlation of 0 indicating there's no relationship. So, and we're going to see, think back earlier when we talked about our null hypothesis, we typically said there were no relationships, okay? So we're going to come back to that. So know that if our correlation coefficient is 0, then there's no relationship. So then the next question is, what does it mean if it's a +1 or a -1? So the variables correlate positively toward the +1 side when we see that as one variable increases in size, the other variables show some systematic tendency to also increase in size. Okay, so typically we would think that the higher your GPA, maybe the more time you spend studying. Okay, or and I'm just throwing stuff out here. Maybe the more strikes you throw as a pitcher, the more hours you spend practicing after school. So as one increases, the more practice you have, then we would expect you to be able to throw more strikes as a pitcher. That's a positive correlation. On the other hand, when we have a negative correlation, this is when one variable increases in size and the other shows some systematic tendency to decrease in a uniform way. And an example here might be looking at buying a used car. The more miles on the car, then the lower the price tends to be. Okay, so that's a negative correlation. But the idea is that we see these things happening in general, uniform manner. The two variables are said not to correlate when, as one variable increases, the other shows no overall tendency to increase or decrease in a systematic way. Okay, so we're going to see that some may or may not increase. As students eat lunch in the cafeteria, does it correlate to the fact that we see higher scores on state math tests? Probably not. Maybe it's the simple fact that we have new lunch providers and lunch is better in the cafeteria. And at the same time, we also have introduced some new intervention programs, and our students who used to be struggling are getting better. So the two things may be happening simultaneously, but it doesn't mean that they correlate together. Okay, and we'll explain that a little bit more later toward the end of our little presentation here. So the first thing we need to do is to graph the relationship between variables. So we're going to visually inspect what we're wanting to see, and then we're going to do the math with it. Okay, and so in just a second I'm going to break away here and we're going to go to an Excel sheet. I'm going to show you some Excel tools that will help you, but let's consider some X and Y variables here. Okay, say you're a teacher and you want to know if there's a relationship between your students' attitudes toward math and their achievement on a math test. Okay, so you have more than 100 students. Depending on which state you may be, you may have as many as 180, 200 students in a day. But let's say you have more than 100 students. You want to take a sample of 25 students, and you're going to give them a questionnaire and figure their scores on attitude toward math, and then record their final math achievement scores. So you can do this in Excel, and all you need to do is create a couple of columns. So now you can see that I have taken 25 students here, or 25 students, and I've simply labeled as variable X their attitude toward math on our rating, and then as variable Y their achievement on the last math test. And so I've constructed here what is called a scattergram. And so the first thing we look at and can see on our scattergram, and I'm going to show you how to do this, so let me make this just a little bit bigger. The first thing you're going to notice here is that indeed there is some pattern that we can kind of see, so that as our attitude in math generally tends to increase, so does our achievement in math, okay, as measured on the y-axis. So visually looking at this, we can see that there tends to be a correlation. So that's the first thing we're going to do is there a correlation? So before I show you how to do this, I want to look at what we mean by visually looking. When I say visually looking, what does that mean we're looking at? So let's look back at the presentation. And this is typically what we're going to look for, okay? So you're going to see generally about 4 different types of correlations here. Visually looking at your scatter plots, your scattergram. So what we just saw was generally a positive correlation. Visually we could see there was some type of positive correlation. Now we're going to talk about the strength of that correlation in a minute. But you get the idea here. If it were a perfect line, it would be a +1. As the line starts to spread out, it's going to go down. It would get down to a 0 if our scores are just scattered all over the board. This shows a direct line across here, but really this would look like the scores are scattered all across and you can see no pattern. If we saw a negative correlation, for example, as the miles on the car go up, the price goes down for used cars, then it would look like this. A curvilinear correlation, we really are not going to talk about that at all in this course. That's for another course. But a curvilinear correlation would mean that indeed there's a correlation that as one variable goes up, so does the other, until they reach a certain point. And then as one variable continues to increase, the other starts to go down, or vice versa. This would be a curvilinear correlation. So let's go back to our chart and do a couple of things with our chart real fast. So the first thing I want to show you is just some basic Excel on how we could get this correlation. So I'm going to scoot this chart down so that we don't have it anymore. And then I'm going to show you how to do this. So what you do is you simply highlight the areas that you want to see if there's a correlation. We're going to insert under charts. We're going to choose scatter, and we're just going to choose the first one. Okay. Now you'll notice a couple of things right off the bat here. So first of all our dots are scattered over here. We have all this blank space. So we need to fix our axis values so that the chart fills up. So we can do that under Format, Format Selection. Here's our horizontal value. So if we look at our horizontal value, we see really the lowest is at 40. So let's set that to 40. We're going to go over here to Axis Options, Axis Options. It's currently set at 0. We're going to set it to 40. Okay. I changed my mind. Let's set that to 35. That way we can see where we are. Now the vertical, that's what I want to set to 40. Let's set that to 40. And it goes up to 100. So we're good. We're good to go there on that. So now we can clearly see the chart that I was looking at. Okay, and we can also add our titles. So we can add axis titles. This one, our y-axis is achievement. In math, and our x-axis is attitude toward math. And then we would change our title as well. I always like to put an N. So that whoever's looking at our chart can see that we looked at 25 students. And so if you were to hover over, you would see exactly what we're talking about. Okay, so it gives us our attitude toward math is 80, our x is 80, and our y then is 65, and it's plotted them out for us. Okay, so we have the same chart here. Okay, so now you've got a little bit of an idea on how to create charts in Excel. So now that we can visually look and see that indeed we believe there is a relationship and it's a positive relationship, let's go back to our presentation and learn how we can do this mathematically, and then I'm going to show you how to actually do it in Excel. So now that we're back to our presentation, we visually saw there was a positive relationship. So now we can see that by viewing the Excel chart, we see that there tends to be a positive relationship between the two variables. As attitude increased, so did the test scores. This shows a positive relationship. We don't know if it's strong. We probably shouldn't put strong in there yet until we do the math. Okay. So some more examples of relationships. Okay, so here's a relationship. The one on the left shows our strength, direction, and linearity. Okay, so linearity is talking about, how are they lined up? And we're going to see that on the chart as well. Excel will do that for us as well. So this is a pretty positive direction. It's pretty strong, and it's pretty linear. The middle graph shows a somewhat negative. It's obviously negative. Not nearly as strong. This is going to be closer to a +1. This will be closer to like -7.5 or -7 or something like that. Okay. So there's still a relationship. It's negative, but it's there. This is an example of a zero relationship. This would probably show 0. And you can see it's nonlinear. There's no strength. There's no direction in this relationship. Okay, so that's the importance of scattergrams. So what we technically are looking for then, our coefficient is called the Pearson R. So once we determine that there is a linear relationship, then we can compute our Pearson R to show the strength of this relationship. And I'm going to work through the math here to show you the math, and starting in probably this presentation, all the rest of them, we will look at the math rather quickly because you can do this math in Excel and it's going to start getting a little bit more complicated. But just to show you, I'm going to review the math with you as we go through it. Okay, so don't feel like you have to understand this math completely here. Though I will add that this class and probably one equivalent to after this class, my professor made us do everything by hand for a short time, but I'm not going to do that. So anyway, let's figure out the Pearson R and how to do it. Wrong button. The Pearson R is going to take us back to our sum of squares. Okay, remember our sum of squares was the deviation from the mean squared when we were looking at our univariate distributions. And we had to square them because some of them were negative and some were positive, and when we added them all together, we came up with a 0. And so in order to get away from the 0 to determine that distribution around the mean, we squared those differences. And so our deviation would look like this, where it showed x equals the quantity x minus x bar, our score minus the mean, and our sum of squares was simply denoted the sum of x squared. This is the square of all those deviations. Well, the same thing is for our second variable, our y variable, okay? And so this becomes y equals quantity y minus the mean of y, and then we're simply going to make our sum of y squared, where y is our variable, okay? So we take all those deviations like we did from our x and our univariate. We're going to do that again, but this time we're also going to do the same thing for our y variables and figure out what the mean of our y-score is. So our formula then, again, I'm going to go through the math fairly quickly because I'm going to show you how to do this in Excel. But our formula is the sum of xy divided by the square root of the sum of squares for our x variable times the sum of squares for our y variable. Whereas, and this is where it starts getting a little complicated. It's not complicated if you just look at it. The sum of squares equals the sum of all our x's squared minus the sum of x's over n, and the same thing for y. And then xy equals the sum of x times y. And notice the difference in the big and small letters here. Okay, that's really showing you it's a difference here. Whereas we have the sum of xy, little xy, equals the sum of big X and big Y minus the sum of big X times the sum of big Y over n. So, you can do this. So let's go back to Excel and let me show you what this would look like. Again, you don't have to do this math, but I want to show you the practical way of doing it behind the scenes here. Well, I don't know if practical is the way to do it, but or the way to say that. But you can see I simply took our scattergram data and I've moved it over here so that our attitude and our achievement are still the same. What I've done is I have taken a column here now for x squared. So 66 times 66. I've taken a column for y squared. And I took a column for x times y. Okay? And we're going to sum those up so that we get down here at the bottom. These are our sums. So that we have x, the sum of our x's, the sum of our y's, the sum of our x squared, the sum of our y squared, and then the sum of our x times y. Okay, so you can do that. This is very similar to what we did earlier. It's just the sum of squares we looked at earlier took the deviation from the mean. Okay, this is not quite the deviation from the mean, but you're getting the same idea of what we mean by sum of squares. Our sheets now, where you can see I've put our x and y values into Excel. All we're going to do here now is we're going to say equals CORREL. You can see this returns the correlation coefficient between two sets of data. Whenever you want to use a function, you use the equal sign in the function and then the parentheses. So we want to put our first set in, comma, now our second set. Close parentheses. And it tells us there our correlation coefficient. If we were to break this down to hundreds, it would be 0.79. And that was the same thing we figured out mathematically. So we know that this formula works in Excel just fine. So let's go back to our presentation. So at 0.79, we know there's a relationship between attitude and achievement regarding math. Can we infer this to our population? Remember, we sampled 25 students out of our class, okay? So now we're going back to some of the last things that we have looked at, and that is once we get a sample and find out something about a sample, how much can we infer back to our population? So don't start groaning when I mention confidence intervals and things like that, okay? And significance. We're going to look at that, and this is somewhat easier actually than the z-test that we did, now that you understand that completely. So we need to first of all remember that what we're testing is our null hypothesis, and then we're going to do a test, and then we're going to create what we call the confidence interval, which you already know what that is. Okay, so if the relationship is random, So let's say we want to look at the relationship between ACT scores and height. Then we would expect that there would be no relationship. So any coincidence that you have a high ACT score and a high height, or a low ACT score and a low height, or a negative relationship where you had a high ACT score and a low height, whatever you do, we would expect that to be 0, okay? So what we're going to look then is we're going to look for our Greek letter rho. Remember, when we're dealing with samples, we use English letters, our Pearson R. When we're dealing with populations, we're looking for Greek letters. And in this instance, it's the lowercase Greek rho. Looks like a P, has an R sound to it. So our null hypothesis then would be that rho equals 0. There is no relationship. Our alternative hypothesis, in the case of our math students, would be that students with a better attitude toward math will achieve higher math scores. Okay, so we're going to test our null hypothesis to see if we need to reject it and accept our alternative hypothesis that there is a correlation there. So now we're going to test to see if we can reject or accept our null hypothesis that rho equals 0. So because correlation sampling distributions are not normally distributed, we cannot use a typical z-test. So notice what we're saying here. When we were talking about things like GPAs, ACTs, and height, and IQ, we had a normal distribution, meaning that our 0 standard deviation was the mean of our population, and that we could figure out within 1, 2, 3 standard deviations where everybody was going to fall. Okay. Correlation sampling is not normally distributed, so we technically cannot use that normal distribution curve that we've been using. So we need a special value for correlation for our rho to determine its significance. And then we're going to talk about how we can deal with that fact that correlation sampling are not normally distributed. And we're going to kind of work around that. But let's first start by figuring out how we're going to see if this is significant or not. For this, we need to look at the value of our information sheet, and that's going to be on the next slide. It is included with this presentation. You will notice that once again we are looking at degrees of freedom. This time we're talking about degrees of freedom being 2 instead of 1 because we have 2 variables instead of 1 variable. So if you remember that discussion, we said that we needed to use degrees of freedom when we're talking about samples and trying to infer from our samples to our population. And this time, since we have 2 variables, we're going to use n minus 2 in our little formula. So what we first need to do is, for our degrees of freedom, we have a sample size of 25. Our degrees of freedom for correlation coefficients is n minus 2, and you can see on our chart here we have the 0.05 and 0.01 levels of significance. So our degrees of freedom is 23. So all we need to do then is see what the critical value for 23 at the 0.05 level is, and we can go down. At the 0.05, it's 0.396. If we could round that up to 0.4. So because our R, our rho, correlation coefficient was 0.79, higher than our critical value, then we can reject our null hypothesis that said that there is no relationship, and we can state that R, a correlation coefficient of our value would occur less than 5% of the time randomly. And we would write this P is less than 0.05. In other words, what we're saying is our critical value of 0.4, we have 0.8 basically there's a pretty strong correlation between students' attitudes toward math and their achievement on the math scores. And we can do this with pretty strong confidence, okay? So if we are wrong, let's say we are wrong, we're saying there's only a 5% chance that we randomly picked the 25 smartest math kids. If we are wrong, just to revisit what we studied in the past, then we committed what we call a type 1 error, remember. In other words, we rejected our null hypothesis, we accepted our alternative hypothesis, when in actuality, our null hypothesis was true. So if we're wrong, we're saying that, we're willing to take that 5% chance that this was not random, that we think that there's something here. So as a result, we're going to try to increase attitude toward math in the hopes that maybe math scores will increase. We'll talk about causation, so be cautious of making that statement very strong, but we'll see that there is a relationship there. So if we had a large group of samples drawn from a population, then we'd have multiple correlation coefficients between x and y. So think back, this is just one sample, but what if we have multiple samples? Okay, and we did this earlier when we had multiple samples of, and we figured what we called the standard error of the means. Remember, we looked to see what kind of error we had depending on our samples. We ended up treating our samples all as one large sample. In theory is what we did. You would do the same with correlation coefficients. Okay, we have a sample of 1 here, but if we had multiple samples, we would see that the correlation coefficients would in actuality vary, because we know that there is variability built within samples. If we could get the whole population, we wouldn't need to worry about any of this, but typically we're not going to be able to do that, so we need to worry about samples. And so that's what we're going to look at here. Because we know that correlation coefficients are not normally distributed, in other words, the reason that they would be normally distributed and center around the mean of 0 is if there were no relationship. But we're saying that we believe there is a relationship, so therefore they're all either going to be centered around a high positive number or a low negative number. Okay, so we have to fix this fact that our correlation coefficients are not normally distributed, because if they were, there would be no correlation. So a statistician by the name of Fisher came up with what we call the Fisher Z, and what it does is it transforms our correlation coefficient to an approximate normal distribution. And we can look at the Fisher Z at that point. So remember when we said one standard deviation above the mean, we mean that this encompasses 34% of the population to the mean and another 50% below, so about 84% of the population fell there. Okay, that's what we're talking about here. So we can't use typical z-scores, but we can use Fisher Z's when we're dealing with correlation coefficients. And so the way we do that is by using 6 steps here. And the first step involves what we just did, computing our correlation coefficient. The second step is converting this to a Fisher Z. And so our correlation coefficient, we said, was 0.79. And you can see that our Fisher Z then is equivalent to about 1.07. So now we have converted this into kind of a z-score. And so our formula then for the standard error of the correlation coefficient, or the standard error of our Fisher Z, and I know you're excited to hear the word standard error again, is z subscript r equals 1 divided by the square root of n minus 3. So here we can take our n is 25, so it becomes 1 divided by the square root of 25 minus 3, or 22. 1 divided by the square root of 22 is 0.21. So now, what we do is we go back to our 95% confidence intervals, and instead of multiplying what we did in the past, we're going to substitute our standard error of our Fisher z in there. So z times our standard error z, or at the 95% confidence interval, I told you to remember that 95% had a z-score of 1.96, 99% had a z-score of 2.58. We multiply it by our standard error and get 0.41. The next step is our Fisher z plus and minus 0.41. So it comes out to 0.66 to 1.48. So all we have to do now is go back to our chart and figure out what that 0.66 and 0.148 would be if we converted them back into correlation coefficients. So we're just going to do it backwards. And so what we see then is 0.66 for our lower limit is 0.58, and 1.48, which is closest to 1.47 on here, is going to be about 0.9. So what we're saying is we are 95% confident that the interval for our correlation coefficient will exist between 0.58 and 0.9. Ours was 0.79, so we're right on target with what we wanted to do. So our confidence interval is there, our strength is there, everything is looking good for us. Okay, we know there is a relationship, and we are confident that that relationship falls well within the pattern that we wanted to look at. So we have been working with R, rho. This explains to us how much one variable interacts with the other. So we're saying at 0.79 that there is a relationship between one variable and the other. There is a relationship between students' attitude toward math and their achievement in math. This does not show causality, okay, or causation. It just means that there's common variability that can be accounted for in this relationship. With a correlationship of r equals 0.79, our coefficient of determination is simply r squared. So this would be 0.79 squared, or 62%. Okay, we're going to change this to percent. This means that 62% of the variability in the attitude toward math can account for math achievement scores. Okay, so let me show you how you do this in Excel, because it's very easy. Okay, we're back to our scattergram. What I'm going to do here is I want to show a trend line. So I'm going to select data. Notice when I select it, the little dots all come up. If you select the data and click a right point, we're going to add a trend line. And so we want a linear line. And I wanted to display our r squared. And notice what we just did. So let's move this up. The r squared is now 62. If we were to round it up, it would be 62. That's the same as what we just said, the 62% variability of one is explained in the other. Okay, so that's what you can do on here. You see that it tends to be a positive relationship, and looking at our r squared, our coefficient of determination, we can see that indeed 62% of attitude toward math can help explain achievement in math. And so we're back here, and I just wanted to show you that indeed that matches here. So that's what trendline does in data for you, or in Excel, I mean. All right, so cautions and limitations. Like I said, let's assume you wanted to see if there was a correlation between water ski accidents during a random selection of summer days and compare that to the amount of ice cream sold each day. The cautions and limitations are that one does not cause another. We don't show that. We just show that there's a relationship that exists. Okay? So if we wanted to look at the number of water ski accidents on a lake during any given summer day and the amount of ice cream sold, there's probably could be a high correlation. Does this mean that when people eat ice cream, they typically have accidents? Or on the other hand, does it mean that people who have accidents typically want to eat ice cream? Probably not. What it shows is that there's something else going on here. So typically during a summer day, we would expect a lot of people to be at the lake, and with a lot of people there, they're going to sell more ice cream. Okay, so the two isolated events have nothing to do with each other. So we could run a correlation and see that they might be highly correlated, but it doesn't show causation. Okay, so keep that in mind as you're looking at correlation coefficients. So there is one other thing that I want to just touch on briefly, and that is if we were to look at correlations involving rank, we change the formula slightly. Okay, this is called Spearman's correlation. We're not going to do this. It's out of the scope of our class, but I do want to just let you know that there's something that shows correlation if you involve rank. Okay, for example, what if you wanted to rank or see if there's a correlation between students' rank in their math class and their rank in their English class? Okay, at this point, since we're doing rank order, we could not use the correlation coefficient row. We would have to use Spearman. And again, it changes the formula slightly. So it's out of the scope of what we're doing, so we're not going to do that, but I just wanted to let you know that, again, this is just one more aspect of statistics of why you need to take another class after you finish this one. So with that said, let's look at our module goals. We said we wanted to distinguish between a univariate and bivariate distribution, and that we did. We spoke about all the things we've looked at up to this point were univariate, and now we have two variables, such as attitude toward math and achievement on a math test. Okay, so that would be a bivariate distribution. We wanted to explain the meaning of positive and negative relationships. As one value goes up, the other tends to go up in a systematic way. That would be a positive. And then as one value goes up or down, the other conversely goes down or up in a systematic way. That would be negative. Okay. We construct a scattergram for a bivariate distribution. We showed you how to do that in Excel. Compute the product of moments correlation coefficient row for a bivariate distribution. We went through the math on how to do that, but you can just do the function in Excel, equals CORREL. Determine the degrees of freedom in a test of correlational null hypothesis. This is the easiest degrees of freedom you will see. Once you compute your correlation coefficient, you just take your n minus 2 to see if it's significant at the 0.05 or 0.1 level. Define and compute the coefficient of determination. That is, again, very simple. We just square our correlation coefficient. And that tells us the amount of variability that can explain one variable to another. We finished by talking about the fact that correlation does not imply cause and effect. And then right before we finished, we spoke about computing confidence intervals using the Fisher-Z and working in and out of that chart, looking at the corresponding correlation values to the Fisher-Z scores. So anyway, that is an introduction to statistical methodology. The very first one typically done correlations. We will move on in our next module and look at a different way we can see, test how things are related.